Hello everyone. One of the topics in vibrations that is very important is a critical speed of rotation or RPM for a shaft. So if you have a shaft and this shaft has a disc or gear or anything on it and it is spinning like in this picture and it is mounted on two bearings here and here, this RPM of this shaft can you operate it at a number that is not close to what we call the critical RPM or the critical speed of the shaft, because if you do, then resonance happens and the lateral deflection of the shaft, okay, this lateral deflection here shown by Y, it can be what? Very, very big, which can lead to the bearing failures, and it is going to create permanent damage and deformation to the shaft. So in reality, when you design a shaft, the first thing is you make sure that your operating RPM should be what? Should be quite a bit above or below this speed that we call the critical rotational speed. And in action, you typically use nominal RPMs that are much higher, much larger than the critical speed. You run it above, way above the critical speeds. And if you have to slow down the RPM and go to numbers below this omega n, basically you have to pass this omega n, right? Then you make sure passing through this critical speed is happening very fast and you don't run the shaft at those speeds for a long time. Okay? So in reality, as I said, omega nominal is going to be way bigger than omega critical, and if you have to pass through it, you do it in a very fast time. Okay, so how do we calculate this critical speed? Let's talk about that. So here I have shown you a shaft with a disc on it that has a mass that is not at the center of the disc. So the center, the geometric center of the disc, which is going to be on the shaft, is this point here. You might call it O. But the center of mass of the shaft is at this point G, and there is a distance between G and O called eccentricity, and show it by this letter E. Okay, so let me highlight this for you. And this eccentricity is very important. The bigger it is, the bigger this centrifugal force of the disc is going to be, and the bigger deflections you're going to have. So in here, this centrifugal force, if you show it by Fe or maybe Fc really, is equal to m times y plus e omega squared. Now, what is that one? So remember, the centrifugal force in general is m times r times omega squared, and r is the radial distance from the center of mass to the axis of rotation, and as you can see, that's this distance from here to here, which is y, the deflection of the shaft, plus the eccentricity. And you might say, where does the deflection of the shaft come from? That comes from the weight of the disc or the gear or the forces that are on it, right? In reality, when the shaft is very stiff and this load is not too much, that y might be very, very small, and you can even not see it with naked eyes, right? Or very hard to see. But when the shaft is not as rigid, or the load is too much, or the weight of these components are too much, then that y could be big enough that you might be able to see that, okay, or sense it very easily. So here is that radial distance, and this is that centrifugal force, right? Now, how do we go about writing a formula for calculating this y? Because as I said, y is the deflection due to the load being applied to the shaft. So, as you know from vibrations theory, each physical member, like this shaft, has some spring constant, some stiffness, depending on the boundary condition it has and depending on where the load is applied. So for instance, in this case, if you call it a simply supported beam with the load in the center, then it can have a constant K, and that K depends on the cross section of the shaft or the diameter of the shaft. It depends on the Young modulus. It depends on the moment of inertia and so on, right? And we have these different scenarios, different formulas for K that you can see in your solid mechanics or your vibrations book if you look at them. So all you need to do is to just look them up at the end of your vibrations book or solid mechanics, and you see there are lots of them here. Like this case, you see there are scenarios for like cantilevered beam with load at the end, somewhere in the middle, simply supported beam, load in the middle, and you see each one has what? Each one has a spring constant, which, as I said, depends on the dimensions, depending on the material, and the length and these distances. So, and maybe in one of my future videos that I make, I basically derive a few of them for you so you see it better. But right now, if we assume that at the moment there is a spring constant K for this configuration, then the restoring force of this shaft that want to bring the shaft back to the horizontal position is going to be K times Y. So if I have equilibrium at this position and the system basically keeps spinning like this, so this shaft is basically curved like that, then the centrifugal force Fc should be the same as your spring force K times Y. And so from here, if you solve for Y, you get what? You get this equation that you can see. So you see the Y, the deflection that you have depends on E. As I said, the bigger the E, the bigger the Y. So you see it's E omega squared divided by K over M minus omega squared, right? So if you know the K, if you know the mass of the disk, right? If you know the operating RPM, and if you know the eccentricity, you can calculate how much deflection you have. And it's interesting, if you look at this formula, depending on how much omega you have in comparison to the square root of K over M, which we call it the natural frequency or the critical speed of the shaft, then you'll see that the Y, the sign of the Y will be different. For instance, if omega is exactly equal to omega n or square root K over M, then this denominator will be 0, and so your Y, as you can see here, is going to have this vertical asymptote. It's going to be very large. So you're going to have very large deflections when the operating RPM is the same as the critical speed and there is no damping in the system. Okay, that's the resonance. That is the speed you want to avoid running at or even close to. Now, if, on the other hand, omega is bigger than omega n, okay, so you are on the right-hand side of omega, this is what I said in reality you do. You run it at bigger than RPM. Then look at the sign. What is going to be the sign of Y? So this denominator is going to be negative this time. This denominator is going to be negative. The numerator is always positive, so the whole Y is going to be negative. Okay, and you can see it here that the Y is what? Negative. On the other hand, if you run it at RPMs less than the natural frequency, denominator will also be positive, so Y will be positive, and this is what you can see here. Okay, so which side of the axis, the center of the disk, is going to be the geometry center, and also G, the center of mass, whether it's positive Y or negative Y, that depends on side of omega n you are operating at. Are you operating above it or below it? Okay. Now let's work a little bit more on this formula for omega n. See if we can find an alternative for it. And for that, we look at a static scenario right now where the shaft is not spinning and the disk is on it, and the disk applies the load W, and the K, the spring constant we talked about, is multiplied by y of statics. The static deflection at the location of the disk is going to be the upward force, which has to cancel W. So these two forces have to be equal, and you know why statics, we can basically determine them from our solid mechanics knowledge. So Ky static, the spring force, is equal to the W. From here, if you solve for y statics, it's going to be W over K or mg over K. If you bring this g to the denominator of y statics, then y statics over g is m over K. And remember, omega n is the square root of K over m, or the reciprocal of this. So I have to take a reciprocal from both sides of this equation. And so it is going to be g over y static, which is the same as K over m. So I can also find my omega n by square root of what? G over y static. So this is an alternative formula for calculating the critical speed of the shaft. Now, let's look at one simple example here. So here we have a shaft with a disk with weight W on it. The shaft has a length of L, which is equal to A plus B. So the disk is not exactly in the center. It is not in the center. The Young modulus is E, and the polar moment of inertia is I. And it is spinning with angular velocity omega. We want to know what is the critical value for this omega. Okay. So from solid mechanics, we can calculate the y statics for this configuration of simply supported beam with A and B not being equal. It is going to be A squared B squared W over 3EIL. And from this formula that G over Y static square root is omega n, we plug that in and we get our beautiful what? Omega n here. So if we want to run this omega, it better be what? It is better be quite a bit bigger than, I don't know why my stylus does that. It has to be way bigger than this formula here, okay? That is the critical speed. We don't want to run it. And now you might say, well, what if you have more than one disc or one gear on the shaft, which happens most of the time. If you look at a transmission, it has a bunch of gears, right? So what about that? In that case, we can still use this formula, but we have to use what? We have to use superposition. So we look at the effect of each and every one of them and we combine. Now, how do we do that exactly? Let me explain. So here, let's consider we have three disks, W1, W2, W3, and the static y's they generate are Y1, Y2, and Y3, okay? Then, or in this case, actually, y's are dynamics y's, not the static y's. Y's are in dynamic scenarios. Okay, but they are this distance from the center of the disk to the axis of rotation. So the kinetic energy of the system, if you neglect the kinetic energy of the shaft, just comes from the disks, is going to be summation over I of what? 1/2 mi vi squared, where vi here is the vi of the centroid of each disk, and that is equal to yi times omega n. Now you might say, why omega n? Because here I assume the system is operating at what? At the natural frequency, and I want to find it. So here I assume that the omega that the system is operating at equals what? Omega n. Or if you want, you can say that the system does not operate at omega n, right? But it is in simple harmonic motion. And in harmonic motion, as you know, the magnitude of V is equal to the magnitude of Y, right, times omega n. So here, This is what we have, and again, what did we neglect? We neglected the inertia of the shaft itself. Can we add it? Absolutely, but here for simplicity we are just neglecting that. Okay, now I'm gonna write these mi's as wi's over g, and the reason is the w's are given. So this is the kinetic energy of the system. The strain energy of the system, which is the potential energy, is given by 1/2 wi yi. Okay, and I assume you know that from your solid mechanics, right? It is 1/2 of the strain force times the displacement, right? Or 1/2 in general sigma epsilon, you might call it, per volume, but the whole thing is going to be 1/2 wi yi, and you know where that y 1/2 is coming from because it's linearly increasing from 0 to yi. So now, if you use the Rayleigh's method, and as I said, I have to create a video on this Rayleigh's method, and I'm going to do that for you. If you set the potential energy equal to kinetic energy, because you assume that there is no waste in the system, there is no waste of mechanical energy, there is no non-conservative force, then you can find a formula for omega n under this scenario. Square root of g times summation over I of wi yi divided by summation of wi yi squared. Okay, and this is going to be the omega n for this scenario where you have all of these disks, okay, and all of their y's. So let's solve an example from this. So here we have a shaft mounted on bearings A and B, and the shaft has an overhang here, and this disc number 2 is mounted on overhang at the end of it, and disc number 1 is mounted somewhere not exactly in the middle, 6 from one side, 4 from the other side. The shaft is made of steel with a Young modulus of 30 mega psi, diameter of 3/4 of an inch, which makes your polar moment of inertia to be 0.155 inch to the 4. You want to find the natural frequency of the shaft for this configuration. So what do? Here you do what? You do superposition, because in order to use this formula, what you need to find are the yi's, because g and w's are given. So what you need is yi. So what would you do? You determine the yi's for each one of these disks, and for that moment you neglect the other disk. So you use the superposition principle, right? And you say what? You say, first, let's assume that I only have weight W1 on it, and this W2 is not there. So if this W1 is on the shaft is going to deflect like this. Okay? And how much is going to be the displacement under the locations of W1 and W2, under the centers of W1 and W2? Where for W1 from solid mechanics, from your knowledge of solid mechanics, W1 is going to be Y1 is going to be W1BA over 6 DEI D squared minus B squared minus A squared. Where what is D, what is A, what is B? D here is the total length between the bearings, and A and B are the distances of W1 from the two bearings. So you can find Y1 for that, and this gives you the displacement under load W1. Then how would you calculate W2 for that scenario? Here we use an approximation. We find the slope angle of the beam at point B, so we find this slope angle. Now it's not as bad, it is probably something like this, and this angle here we call it theta B. You know, theta is the derivative of y with respect to x. So if you know the y function for this beam, if you know y as a function of x for this beam, then theta from your solid mechanics knowledge is y prime of x. And here we had the formula for y of x from solid mechanics. We just plugged in this point for x, which is x equal a if you start x from the left side. Okay? And so we can find the derivative of this y at x equal d, which is this point here, and that gives me that angle theta. Now if I multiply that theta by this length, knowing that that theta is small, and so the theta is the same as its tangent, because these slopes are small thing. So if we approximate it by tangent of theta b, then tangent of theta b is going to be how much y2 is going to go up this distance, right? And divided by the length of the overhang, which is this distance, and that is 3 inches. So if you multiply 3 by tangent of theta b, which is the same as theta b, you can find y2, which is only under load W1. And that is what we have done here. C, which is that distance, times sine of theta b, or theta b in this case. And if you do that and solve for it, you're going to get 768 EI, but upward for point here for the center of the first disk. It is going to be a similar number, but it is going to be downward, as you can see, right? You see this one goes down, that one goes up. This is the y1 and y2 under what? Under only W1. Now here we go and look at the scenario for neglecting W1 and looking at W2. Now, one thing that is very interesting here, if you look at the book by Martin, which by the way, again, the pictures and the equations here coming from his book on kinematics and dynamics of machines, one thing interesting that he mentioned, and you have to go through it and read it a few times to understand it properly, is instead of considering for W2 alone that W2 be downward, and you know when W2 is downward, how is your beam gonna deflect? If W2 is downward, which it is, right, then the beam is gonna go, this part is gonna go down and this part is gonna go up like this, if it's only W. So this time, whatever deflection y2 you get here should be negative or downward, and y1 should be positive or upward. And so this deflection should cancel the previous one, because in the previous scenario, as you can see down here in red, it is exactly opposite of that. And the reason for it is one of them is between the bearings, one of them is outside the bearings on the overhang, right? But keep in mind that, first of all, here W1 is the bigger one. And when they start basically moving, so when you start this beam, because W1 is the dominant one, right? The overall shape of this is going to be barely touching down here and maybe a little bit going up there, okay? Now, the effect of W2 is what, really? Let's take a look at the effect of W2. Since this guy is lifted upward, when it starts spinning, the centrifugal force of this disk is going to be upward. So if you want to approximate these dynamic y's that we have over here with their counterpart static parts, you better what? You better look at what they do in dynamic scenarios. And for that reason, since the centrifugal force is upward, instead of finding y1 and y2 under a W2 that is downward, you better do it under a W2 that is what? Upward. That is going to be a better approximation of your dynamic deflections, right? Instead of going and doing it pure static. Because the system's behavior when it's spinning compared to when it's not spinning is quite a bit different. And remember that, again, these y's that we are using in this Rayleigh formula, these are dynamic y's. Here we have assumed that we have spinning. And you might have asked, why are you approximating your dynamics one with these formulas from statics and solid mechanics? You are right. So if you want your, that's because that's the only thing we have, okay? If you want to find these k's or y statics, you have to resort to your what? You have to resort to your solid mechanics knowledge. And here, if you want, you can rewrite this formula here. You can rewrite this formula in terms of ki's instead of yi's. But again, those ki's are coming from static scenarios, right? Not dynamic ones, as we just discussed. So here we are approximating dynamics y with statics, and to do a better job, we better consider W2 being upward. If we do that, then y1 for a W2 of upward, you're going to get a similar behavior. You're going to get y2 to be upward and y1 to be downward, and these are the two formulas that from solid mechanics you can get them. Now you combine this y1 downward and that y1 downward, you get this total y1 downward this much, and then you combine this y2 upward and this y2 upward together, and you get this much y2 upward. And now if I use that y1 and that y2 into this formula and plug it in and plug in for the numbers for E, right? And for I, then I should be able to what? Calculate exactly the values of y's and plug them in. And finally, you see that your critical speed is going to be 3530 RPM. Of course, the number you get out of here is going to be in radians per second, but here we converted it to RPM. So when you do this kind of thing and you want to find these y's from solid mechanics textbook, you better be careful and look at the behavior of the system under the centrifugal forces. Okay, yeah, because this guy is going down, so the centrifugal of this is this way. The centrifugal of this weight 2, which is lifted up a little bit, is that one. So they are helping each other to increase the y's. They are not canceling each other, okay, when they are spinning. Finally, remember that here we neglected the inertia of the shaft. If you want to include it, you can add it to this formula here, although it's not as simple, because if the shaft alone is spinning under this arbitrary function y of x, right? So if it is spinning like this, finding the kinetic energy of that is not as simple. You might say the kinetic energy is simply 1/2 I omega squared. No, it's not. This is assuming there is no deflection. Because when it is deflecting, the I of this shaft about this axis is not this simple pi d to the, here, where is it? Pi d to the 4/64. It's not this much. Remember, we have to calculate it under dynamics. So now you have to bring element by element. You have to calculate each small element dx here. Look at its y of x. Calculate its velocity, which is going to be y times omega, the whole thing squared, times dx. So it is going to be like this. And this y, remember, this is y of x, times omega, this whole thing is squared, times 1/2, and then the mass of that element, which is going to be dx times what? Times mass per length, which if you assume it's uniform, it can be the total mass, m, divided by L, or W, divided by G, which is mass, divided by L. So this is the mass of that element. And then you have to integrate this guy from 0 to L. This is the term that has to go there, not this one. Okay, so if this W of the shaft, is not negligible, then you have to calculate this. And so there is a formula in vibrations which is an approximation for using Rayleigh method with this y of x, and it says it's called the Dunkerley equation. It says the critical speed of a shaft that has a bunch of disks on it, if you call it omega n, and omega s here is the critical speed of the shaft alone without any masses, then you can combine these into one formula, and 1 over omega n squared is 1 over omega s squared, where omega s is the critical speed of the shaft alone with no masses, and these omega i's are the critical speed of the shaft if the shaft is massless, but it is supporting weight wi in general. Okay? Yes, so if you want to combine them and come up with the total critical speed, the resultant, not total, the resultant critical speed of the shaft, you can combine all of those, the omega i's and this omega s, the inverse of their squared, and that gives you the inverse of omega n squared, and this is an approximation. Okay, it's not the perfect, but it's a good approximation for critical speed of the shaft. So it's called the Dunkerley's equation. Okay, so hopefully I could introduce you to the basic idea of that each shaft has a critical speed. You need to calculate it, and you need to avoid it when operating. So thank you so much for your attention. I'll see you in the next video.